Section 6-5 here is on limits of indeterminate forms. And we'll use L'Hopital's rule, or what you've seen so far. We're using L'Hopital's rule to evaluate those. The objective of this section is given an expression with an indeterminate form. Find its limit using L'Hopital's rule. All right, and if you recall, we've already seen the quotient and the product indeterminate forms, and how to use L'Hopital's to evaluate those. And now we're going to look at the difference and the power forms, and look at how we can use L'Hopital's rule to help us evaluate those ones. Now to do that, we need an additional property here that we'll see. And this property here is what's called the limit function interchange property. Limit function interchange. In other words, it allows you to interchange a limit and a function. Swap the order that they're in essence. Interchange a limit and a function. And we'll need this in order to use L'Hopital's to help us evaluate the power form is what we'll use this for. In fact, that's the only time you'll need to use this. If your function starts out in the, or if your limit starts out in that power form, then we're going to have to use the limit function interchange property. Here's what the property says. It said, well, I guess I'm going to show you the whole thing here. It says if you meet the following two conditions. So the first condition is the limit as x goes to c of h of x is equal to L. Now, h of x, if you look down there in the conclusion of this, it's talking about a composition here, g of h of x. So h of x is our inside function there. So if the limit as x goes to c of h of x is equal to L, so the limit of the inside function exists and it's approaching some value of L. And the second condition there is that g, this is our outside function, g is a continuous function at L. Now there are two ways that you can show that g is a continuous function there at L. One of those is to use the definition of continuous. Remember, the definition revolves around three parts there. The function has to exist, the limit has to exist, and they equal each other. So that's what it's saying there. If the limit as x goes to L of g of x equals g of L. That's that definition. Or the other way to do it, since we know differentiability implies continuity, you could take the derivative of g and see if it exists at L. Plug in L and see what you get. And as long as that exists, then you're differentiable there, and which means that you are thus continuous there. Either one of those methods there can be used to show that that g is continuous at L. All right, so if you meet those two conditions, the limit as x goes to c of h of x is equal to L, that's the first condition, and then secondly, g is continuous at L. Then the conclusion is this, that the limit as x goes to c of g of h of x is equal to the limit as x goes to c of, or excuse me, is equal to g of the limit as x goes to c of h of x. All right. Notice that what's happened there is we've been able to interchange the limit and this function g. On the left here, it's the limit first, followed by g. And over on the right side, you have g first, followed by the limit. So we've interchanged those two. We've swapped the order that they're in. This is why it's called the limit function interchange property. You can interchange the limit with that function. You can use it either way. If you have g of the limit, which is actually how we're going to be using it, you can rewrite this as the limit of g of that quantity. All right? So that's the limit function interchange property. Two conditions to show that we meet, and then we can use the property there. All right, let's see how we can use that here in example number 3. Example 3 says to evaluate the limit as x goes to 1 of x raised to the 1 over 1 minus x. All right. So let's see what this is approaching here if we let x go to 1. Oops, I was going to do that in another color here. If we let x go to 1, then the base here is taking on a value of 1. The base is just x, so it's going to 1. And the exponent there, I have 1 divided by 1 minus 1. 1 divided by 0. 1 divided by 0 is infinity. 1 to the infinite power, that's one of our 3 indeterminate forms that's in the power form. All right, so that means we got to do a little bit more work in order to find out what this is equal to. So to do that, I know that if I'm going to use L'Hopital's, I have to get this thing in the quotient form. And we're not anywhere close right now, so we got to do a little bit of work to get there. So the first thing that we do is we say that L is equal to this limit. We're going to say L is equal to the limit as x goes to 1 of x raised to the 1 over 1 minus x. You could do that on the same line there. I'm just going to separate it just so you see how we write this out. L is equal to that. And then we're going to use logs to help us to deal with this because of the fact that I've got this in this power form right now, and I need to get it into the quotient form. And I have a rule for logs that allows me to rewrite a power like this as a product, and I can go from the product to the quotient form. That's my game plan here that we're going to follow. So let's take the log of both sides. We're going to use natural log, of course, to do this. The natural log of L is equal to the natural log of the limit as x goes to 1 of x raised to the 1 over 1 minus x. Now, what I need to do in order to use my log property, that's the whole reason for using logs here, so I can use one of my log properties, I need to interchange the natural log and this limit. I need to switch those two. So in comes the limit function interchange property. Okay? So let's go through the limit function interchange property. All right. So the limit function interchange property, I want to interchange the limit with that natural log. So I got to show that I meet two conditions in order to use this property. The first condition was that the limit of the inside function has to be approaching some value L, which we've already stated that we're going to say that L is equal to the limit as x goes to the 1 over x. That's the inside function here. Okay? We've already stated that L is equal to the limit as x goes to 1 of x raised to the 1 over 1 minus x. So we've already got that part. That's the easy part. The second part isn't too difficult. The second part is about function g, which in our case is it's the outside function, which in our case is that natural log function. And you had to show continuity at this value of L. All right. So the easiest way to do that is to take the derivative of this outside function. So we're going to do it that way. That I know that the derivative of the natural log of x is equal to 1 over x. And that's for all x greater than 0. So that means it's differentiable for all x greater than 0, and thus it's continuous for all x greater than 0. So differentiability implies continuity, and we get that this thing is continuous for all values of x, regardless of what L is there. Turns out that this function is going to be continuous. Which, this is the same thing that's going to apply for every single problem that we do. So for that reason, I'm doing this once for you to show you why we meet the limit function interchange property. You should understand why that is. But from now on, we're just going to use the property because we know both of these are going to hold every single time. The second one is always going to be the same thing every single time. It's the outside function is natural log. The first one, of course, is going to change as far as the limit is concerned, but we're always going to be setting the L at equal to our limit, and so the first properties are always going to hold. So our conclusion for this is this. Thus, the limit as x goes to 1 of the natural log of x raised to the 1 over 1 minus x is equal to the natural log of the limit as x goes to 1 of x raised to the 1 over 1 minus x. Again, we have what we have in our problem is in this second form right here, and we want to rewrite it in the first form. We want to interchange the limit and the natural log. Okay? So let's continue on here. We'll just draw an arrow down to here. Again, this is going to be the case every single time, so you will not need to illustrate why you meet that property every single time for me because it's going to be redundant over and over again, the same thing. So we've done it once together. That's the last time that you need to do it on your assignment, at least. You should be able to explain why it meets those conditions on a test, but that is sufficient for our assignment. So I can interchange the limit and the natural log. So that's what we've done here. All right, now that I've got the natural log of this power, I can use my power property for logs. It says that I can rewrite that as 1 over 1 minus x times the natural log of x. And now I've rewritten this limit from a power form to now a product. So let's check to see what form this is in as a product. If I started out indeterminate, I better still be indeterminate here. Let's see if we end up that way. I have 1 over 1 minus 1. That's 1 over 0. That's heading towards infinity. And you have the natural log of 1. Natural log of 1 would be 0. That's our product form of an indeterminate. We already saw in the first half of this section that if I get this if I'm in the product form, I can rewrite this as a quotient. So we're getting close. I still got to do a few more steps before I can actually use L'Hopital's though. I guess technically it's one step and then just making sure you're indeterminate here. You've now got to rewrite this, and I think it's pretty obvious for this one which way to rewrite it. I'm going to put the natural log in the numerator and 1 over x in the denominator. 1 over x times natural log of x is the same as natural log of x divided by 1 minus x. I would say that it's going to be pretty much this same setup every time for you, that you're going to want to put the natural log in the numerator as opposed to putting the reciprocal of it in the denominator, because that becomes a pretty complex derivative. And for what we're trying to do to simplify the problem, that's probably not going to be the method you want to use. So probably going to find over and over again that you want the natural log part in the numerator. But double check to see what form you're in. In the numerator, as x goes to 1, natural log of 1 is going to 0. In the denominator, as x goes to 1, 1 minus 1 is 0. Hey, look at there. We are in the quotient form of an indeterminate, which now that I'm in that form, I can apply L'Hopital's rule to this limit that I have over on the right side. So I still have the natural log of L. I still have the limit as x goes to 1, but now using L'Hopital's rule, L'Hopital says just take the derivative of the numerator, which is 1 over x, and divide it by the derivative of the denominator, which is going to be 0 minus 1 when I take the derivative of those two parts, but that'll just be a negative 1. And again, if you can, I would suggest that you simplify this before you start trying to evaluate that, which I can see that I can simplify this for sure. Probably, I really don't have to in this case, but I'm going to simplify it as a negative 1 over x. Just move that negative 1 to the out of the denominator there. And now look at what this is approaching here. This is approaching a value of, if I let x go to 1, it'll be a negative 1 over 1, or that's a negative 1. Now, that's not our answer. It's not the limit that's equal to a negative 1. Remember that we were trying to find, let me go back up here, we're trying to find this limit right here. This limit right here, which is what we defined as L. We said L is equal to that. So down here, we don't have that L is equal to that. We have the natural log of L is equal to that. This is why we keep writing down this natural log over on the left side so we don't forget this. It's the natural log of L that turns out to be a negative 1. So if you exponentiate this to base e on both sides, you'd have e to the natural log of L is equal to e to the negative 1. You can also use the definition of a log to help you simplify this, but e to the natural log, those are inverses, so they basically cancel each other out. We end up with L is equal to e to the negative 1, or that's 1 over e if you want to write it that way. There is our limit. You can see that these ones that involve the power form of an indeterminate form definitely take a few more steps to get to the answer. But you basically go from the power form and get it into the product form, and then from there get it into the quotient form, and then from there use L'Hopital's. And then once you get that, you still got to go back and find out what L equals. You'll have what the natural log of L equals. So there's a lot of steps involved in this one. Let's take a look at one more example. They don't give us another example in the book, so I'm going to give you one out of the problem set there. If you look at number 30 there, they give us the the limit as x goes to 0 of 1 over x minus 1 over the sine of x. All right. So you've seen the quotient form, you've seen the product form, you've seen the power form. The only one left here for us to consider is the difference, which is what you're going to have here. If I let x go to 0, 1 over 0 is infinity. And sine of x, 1 over sine of 0. Sine of 0 is 0, so that's 1 over 0. That's also infinity. Here's our difference form. Now, I can rewrite this. And in particular, I can get a common denominator to get this directly into the quotient form. I'm going to multiply this first fraction here by the sine of x over the sine of x. I'll multiply the second fraction there by x over x to get a common denominator. So I'll have the sine of x over x sine of x minus x over x sine of x. Okay. And now that I've got a common denominator, just add those two together. You could have done this all in one step, of course, but we've got the sine of x minus x in the numerator over x sine of x in the denominator. Now, if we started out with that indeterminate form, we should still be indeterminate here, but double check that you are. If I let x go to 0, sine of 0 is 0, minus 0, that's 0. In the denominator, you have, as x goes to 0, you have 0 times sine of 0 is 0. That's 0 times 0 is 0. By the way, you need to evaluate that out completely. If this had turned out to be 0 times infinity in the denominator, then you got another mess to deal with. In fact, you wouldn't want to even try to go through the problem that way. All right, you'd want to back up and try again. But because of the fact that it's not, it's 0 times 0, we get 0, of course, for that. So I can continue on here. We're all ready for L'Hopital's rule then. We're in that quotient form for an indeterminate. So the limit as x goes to 0. Take the derivative of the top. Derivative of sine is cosine of x. Minus derivative of x is 1. In the denominator, if you got a product, you got to follow product rule then. Derivative of x is 1 times sine of x plus x times derivative of sine is cosine of x. And let's see what form we're in. Obviously, if there's something you can easily simplify, do so, but I don't see anything here that we're going to easily simplify. So as x goes to 0, cosine of 0 is 1, minus 1, that's 0. And in the denominator, you have sine of 0 is 0, plus x, which is going to 0, times the cosine of 0, which is 1. 0 times 1, of course, gives us 0, so we still have 0 plus 0 in the denominator, or 0. So we're still indeterminate. So I'll use L'Hopital's again. So in the numerator, derivative of cosine is a negative sign. In the denominator, you've got derivative of sine of x is cosine of x for the first part of that, plus x times cosine of x, that's a product, so use product rule here. Derivative of x is 1 times cosine of x, plus derivative of, or x times derivative of cosine of x is a negative sine of x. And if you can simplify this, which I guess there's a couple things I can combine here. I don't know that it will help me at all in evaluating this, but I got cosine plus cosine in the denominator, so I'll rewrite that as 2 cosine of x, and then minus x sine of x. All right, and let's see what value this is approaching. So if x goes to 0, sine of 0 is 0. And in the denominator, we have 2 times cosine of 0. Cosine of 0 is 1, of course, so that's 2 times 1. And then minus 0 times sine of 0, that's 0 times 0, so that's minus 0. So this approaches, or this takes on the form of 0 over 2. That is not indeterminate. It's only indeterminate if it's 0 divided by 0, or infinity divided by infinity there. This is equal to 0. 0 divided by any number other than 0 is 0. So it turns out that this limit is approaching a value of 0. There is our answer. All right, and that's the end of this second half here for us.